Hello everybody. We're still talking about distillation, and in this video we are going to talk about one case that we face a lot, and this case makes the distillation kind of tricky and difficult. um, and we will see how we can deal with it and what are the approaches that we can follow to do distillation in such cases. But first, I want to quickly review the shape of the TXY envelope and the XY diagram that we use to kind of understand how distillation takes place. So this is the liquidus curve and this is the vaporous curve, and this is the region where the mixture in this region would split into two phases in equilibrium: the liquid phase with composition different from the vapor phase. And this is the basic idea of distillation, that we can make stages that are consecutive, and each stage is changing the composition, increasing the composition of one of the components, and keep increasing until we reach very high concentrations up to maybe 99 point something percent. And this is what we did in McCabe-Thiele diagram when we drew the operating curve with the equilibrium curve here. I mean the operating lines with the equilibrium curve here. And we saw how the shape of the equilibrium curve dictates it, or affects the number of stages that we use. And this was something that what we discussed before. One thing I want to kind of make clear is that the vaporous curve and liquidus curve do not meet in any point on the curve except for the 100% and 0%, which is the compositions of pure components. This represents pure component which doesn't have a boiling range, but it has a boiling point. So this is one difference between the mixtures and the pure components. So this is the ideal shape, or the close to the ideal shape of the TXY diagram and the XY diagram. There is or there are many shapes of deviation, but there is one shape of deviation from the ideality which is very famous, what we call the azeotrope. And by the azeotrope, we mean that the liquidus curve and the vaporous curve would meet or intersect at a point different from the pure components that we mentioned before. So this is what we see here. This is the vaporous curve, and at this point the liquidus and vaporous curve intersect, and it happens here. It can be at a boiling, or at a temperature lower than the boiling point of the two components, or higher than the two boiling points of the two components. So it might be called a minimum or a positive azeotrope in this case, or a maximum or negative azeotrope in this case. So when we have a case like this is a kind of a very big challenge to distillation, because what happens here is that the mixture at this composition behaves as a pure component. So there is no wet region here. You have just a point where the vapor will, or a liquid would evaporate with the same composition. So no matter how many stages that we use in this case, it's not gonna change anything in the composition. So it's like having a pinch point in the diagram, or in the TXY diagram, and the same here. You can see here in the TXY or the XY diagram, we cannot put the McCabe-Thiele diagram on this shape. We can put it in this part of the diagram because this is what we're used to, or in this part of the diagram because this is what we know. So there is gonna be a limit to distillation. If I start from here, I can reach this point, but I cannot exceed it. So when we have isotopes, and by the way, isotopes are common in mixtures, especially for the polar mixtures, because the level of unideality is very high in such cases. So what I want to discuss now is how we deal with such cases. If I have an isotropic mixture, how we can get it to separate, or we can separate the components in such cases. So there are three approaches which are the most famous approaches. There might be others that I don't know, but these are the three most famous approaches that I know of. The first is what we call the azeotropic distillation. The second is extractive distillation, and the third is using membranes. And in the third case, we do distillation until we reach the maximum purity that we can achieve using distillation, and we can go further by using membrane, so we can separate the two components based on the solubility in a membrane or based on the molecular size. Whatever the method that we're gonna use, this is gonna do the extra step that we cannot achieve using the distillation or the normal distillation. Uh, I'm not going to go into details of this because this is not the point of this video. I just want to make the difference between these two methods clear, because it was something that confused me for some time. So I believe it is important for the audiences to understand what is the difference. Especially they are kind of close or similar in many senses. So what we do is that we add one more component here and here. So in both cases, we add one more component that helps us get through this. And I'm going to discuss in the next two slides what is the difference and what is the purpose of adding this component and what is it doing. So one very famous example of the isotopes is the water ethanol system. So water and ethanol are form a minimum azeotrope at 89 mole percent ethanol and 11% by mole water, which corresponds to almost 95% ethanol. And in many cases, we want to increase the purity of ethanol, for instance, to use it as a fuel grade ethanol. In this case, we have to have 99.5% ethanol at least. So doing distillation will not help to do this. So one thing that we can do is to do what we call the azeotropic distillation. And by this, we mean that we are adding one more component to the system, which is benzene. And benzene forms an azeotrope with ethanol and water, so it's a three-component azeotrope. It's not a binary azeotrope, it's ternary azeotrope. Um, and this azeotrope evaporates at a temperature lower than the boiling point of both ethanol and water. So what happens is that benzene takes all the water and part of the ethanol to form this azeotrope, and it evaporates, so it comes as a top product from here. And the bottom product is the rest of ethanol that is not part of the azeotrope anymore. So what I have here is almost pure ethanol as a bottom product, and the top product that I have here is a mixture of ethanol, water, and benzene as the azeotropic composition. By cooling this down, the mixture kind of splits into two phases, the aqueous phase and the organic phase. The organic phase is mainly benzene with some ethanol and water. And we have another liquid phase that's in equilibrium with this phase, which has this composition. It's kind of rich in water and ethanol with some traces of benzene. So this decanter is kind of one added step one added unit to the column to make sure that we recover or recycle the benzene reach stream as the reflux stream, and we add makeup benzene to compensate any losses of the benzene in the process. So this is what we call the azeotropic distillation column, and from which we got almost pure ethanol, 100% ethanol, and we were able to solve the problem of the azeotrope. However, we have other columns here because we want to make the process feasible. And by making it feasible, we want to make sure that we don't lose any of the benzene that we added, because it's a raw material that's costly. So we use this benzene recovery column. So the function of this column is to use or recover all the benzene that we lost here in this phase, and to recycle it and use it or feed it to the condenser in the distillation column. And this bottom product, of course, there are some ethanol as well. And the bottom product is a mixture of ethanol and water, almost equimolar. We use a distillation column to get the isotropic composition, and then mix it with the feed. So at the end of the day, we have three columns. One, the feed is entering the first column with the benzene, and we're getting ethanol out of the first column, and we're getting water out of the second column. And this is something that we should expect, that we will have more columns because we add more components. So we should expect that we have more columns, not just one column, to make the process feasible. The second case, or the second method, is the extractive distillation. And this is similar to isotropic distillation in the sense of addition of one more component. However, it's different from it according to the function of this component. So the previous case, the component that we added, which was the benzene, was added to make an azeotrope that will extract all the water and leave the ethanol, some of the ethanol with almost 100% purity. But in this case, we add a component that is not volatile, so it has high boiling point, and it has high affinity to water. So it's gonna absorb or extract the water from the ethanol water mixture. So they are evaporating and distillation is going on, but water is not evaporating with ethanol, or it's not separated from ethanol based on the boiling points, but it's separated based on the solubility in the solvent that we have here. Sometimes it's called solvent, sometimes it's called entrainer. Both words are used for the same thing. So the solvent is dissolving the water, and then the ethanol is coming as a top product here, and there is another column for solvent recovery to distillate the water from the solvent, which is glycerin, or some other components might be used, but glycerin is one famous solvent that's used. The solvent is now free from water, and we can recycle it and use it back. And of course, there should be a makeup stream here as well. So this is the kind of difference between extractive distillation and the isotropic distillation. I hope I made it clear. I know it's kind of confusing, but I hope it's not confusing anymore. In the next video, we'll see or we'll solve an example of extractive distillation on Aspen Plus. But before ending this video, I want to kind of quickly revisit the kind of how I know that I have an isotope in my mixture, and I want to show you, if I'm going to do normal distillation like what we did before using Aspen Plus for an isotropic mixture, what we will see. So first, I defined ethanol and water, and the method that I used was NRTL because they are polar components and I'm not using high pressure. To know if I have an isotope, we have different options. The first is go for binary analysis and ask it to go for mass fraction or mole fraction. Let's make it mass fraction and see how the phase diagram will look like. I know that there's an isotope that will appear here, but I just want you to see how it looks like, so you can expect that this is an isotropic mixture. So this is what I meant. It's almost at 95%. If it's in mole percent, it's gonna be something around 90, 88, something like this. So here the two curves overlap, and if we kind of zoom in here, we can see it clearly that the two curves are now overlapping here. So there is no way I can go with distillation further than this 94 point something percent, which is 94.2%. So this is one way I can do this. The other way is to go to simulation environment, and here I define the distillation column, and I have the feed to the distillation column to be just at any temperature and pressure, and almost at the isotropic composition. It's kind of a little before that. And I used a shortcut distillation column with any pressures and any reflux ratio, and I defined it so that I have 99% recovery of ethanol and 1% recovery of water in the top product. And this should correspond to almost 99.9% ethanol purity in the top product. Now, before running the simulation, I want to kind of go for the isotropic search, which is the second method that we can use to check for isotopes. And here I can check for the components that I want to know if they have isotopes. And in this tab, you can see that you have a temperature 78.15, an azeotrope, which is a homogeneous isotope. And by homogeneous, I mean that it is the two components are miscible at any compositions. So, for instance, in this case, we had two phases, so they're not miscible at all compositions for ethanol, benzene, and water. But for ethanol and water, they are miscible at all compositions. So we can know that there is an azeotrope here. So now what I want to do is to see if I run the simulation with the shortcut column, having the feed as an isotropic mixture. So it's giving an error, and there it said that there is an error in the shortcut column, and the number of stages is negative. And this is usually result when it's too easy to separate the light and heavy components. This is the error that is displayed, but this is not the true reason. The true reason is that the shortcut column is not designed to deal with isotropic compositions. So it has an error that corresponds to the very easy separation in normal cases, but if we check the stream results, we'll see that it's giving us ethanol with purity 99.7 mole percent, or with mass fraction it's 99.9. The mass flows is as we requested, that I have almost only 1% of the ethanol to be lost, or 99% to be recovered in the top product. So it's doing all what we want to do. But for the results that we see here, that the number of stages is negative. So if we see this this error, this means that we have a mixture that cannot be separated by distillation. We saw a similar error before when we flipped the light and heavy key components. But in this might be an option. If we do this here, the number of stages would be positive, but the reflex ratio would be negative. So this is kind of a way that we can use to check and make sure that the mixture is isotropic or not. So this is all for this video. In the next video, we're gonna do the extractive distillation example, and in the following, I'm planning to do the rest of the flow sheet, the rest of the column, and do the recycle stream as well, because we haven't discussed the recycle streams in Aspen Plus before. So this is the topic of the next videos, and I'm gonna see you then, inshallah. Goodbye.